Welcome to Lecture 16C, Triple Integrals in Spherical Coordinates, and a set of examples which are a little bit more challenging. Again, this material is covered in section 16.5 of the text, and reading assignment 2, reference material from section 3.2. This is not mandatory reading. The objectives are to understand a select set of more difficult problems from the assigned problems and previous quizzes and exams. And again, the concepts and visualization skills we're dealing with here are the integration bounds for radius rho, angle psi, and angle theta, visualization of bounding surfaces in spherical coordinates, and the differential volume in spherical coordinates. I've got two additional notes here. One is that these examples have already been covered in the lecture before. We looked at some of these examples, if not most of them, in Cartesian coordinates as well as in cylindrical coordinates. But given that we've done those two, we can now basically also look at how you would solve them in spherical coordinates. So it turns out that in many cases, they're much easier to calculate in the coordinate system other than Cartesian. Lecture 16.3 contains worked out examples from the textbook, and you can skip this lecture if you were able to understand the homework examples. Just one caveat that some of these examples I've done in spherical coordinates actually do not exist in the textbook, so they're quite new. So you'll have to pick and choose your way through this lecture as it suits you. Well, as usual, the second slide, just a summary of the slides to follow, and that will be the three specific problems that I've extracted from the textbook. So we'll just move on. All right, so let's take an example then of a triple integral to be computed in spherical coordinates, and this is question 69 from chapter 16.4 of the textbook, or basically reading assignment 3. So since we're dealing with spherical coordinates, the first thing to do is to write out the transformation equations for x, y, and z, which is basically done here. All right, so the next thing basically do is to determine the equation of the upper surface, and this is obtained by taking the equation of the sphere, which is this expression that you see here, and substituting in for x, y, and z into this expression. And if you basically compute the sum of the squares, you will end up with rho, and rho is equal to r. You have a rho squared and an r squared, take the square root, and you get rho equals r. Now the expression for the lower surface, which is this section that you see here, is obtained by realizing that this height that you see here would be basically equal to this radius minus this height. So if you swing this around to here, that r minus height distance would be basically this distance that you see here. So the height z of this bottom surface would be just z equals r minus h. However, in spherical coordinates, if this is the radial vector, then we can basically say that rho, which would be arbitrarily radius pointing all directions with respect to the origin, the angle phi would be the angle that you see between the z-axis and the radial component. Then at this point here, we can say that z equals r minus h, which is this height, is nothing more than rho times the cosine of this angle phi. Now we can rearrange this because we want it in terms of rho. So if you basically divide through by cos phi on both sides, you end up with rho equals r minus h sec phi. Now the intersections between these two surfaces, that is the surface rho equals r, which is this upper surface, and rho equals r minus h sec phi, which is this lower surface, right? That gives you the upper bound on psi. So if you equate the two, r minus h sec phi equals r, and solve for phi, we get cos inverse of this ratio. The lower bound on phi is 0. So we basically start here and we swing phi until we get to this point, which is the intersection point, this angle phi being the value that's computed here, that's highlighted in yellow. And the last is the range on theta. Well, this will be a full circle, so theta will range from 0 to 2 pi. So we can now write everything out that we need in order to be able to solve this triple integral. First of all, in spherical coordinates, the differential volume becomes rho squared sine phi d rho d phi d theta, and the rho squared sine phi is the determinant of the Jacobian matrix. The bounds on rho we've just basically computed. Here's the lower bound. and here is the upper bound. And for phi, the lower bound is 0, the upper bound is this expression here, and the bounds on theta from 0 to 2 pi, which is going once around the circle. 6 integration bounds here, and also differential volume. We have all the information required to do the calculation. All right, so now we set up everything. So here are the bounds inserted. The first bound is with respect to, this here is with respect to d rho, which is r. The second is with respect to angle phi, and the third is with respect to the angle theta. So in this case, basically, rho will range from r minus h sec phi to r. And so that effectively would be the sphere that you see here, which is r, and r minus h sec phi would basically be this pink plane that you see here. So we're going from this surface to this surface. This will be in spherical coordinates. The middle integral is range of phi from 0, which would be this yellow line, and then basically an angle phi, which is what you see here. In this case, basically, r can take on any value, and theta can take any value from 0 to 2 pi. Theta, r, of course, has to be greater than or equal to 0, which means basically we end up with a cone. So we're between this line and this cone. We're between this pink surface and this lower pink surface. And lastly, we're from theta from 0 to 2 pi. In this case, r can be any value greater than 0, and z can be any value, which means we're looking at just a half plane. And this half plane basically is rotated once around the z-axis to make one full circle from 0 to 2 pi. And so what we're doing is we're sweeping out the volume contained within this sphere and this plane. And this is done in spherical coordinates. If you want to look at this in more detail, you can just click on the link that's shown here. All right, let's do question 21. Triple integral. Problem is stated as follows. The volume between the sphere x squared plus y squared plus z squared equals 19. And the hyperboloid z squared minus y squared minus x squared equals 1, and z greater than 0. So we're looking at only at the upper hyperboloid. There is also a mirror image of it in the below the xy plane. So we're interested in the volume contained between this cap and this bowl, as you might say. So again, since we're going to solve the problem in spherical coordinates, here are the transformation equations. So we need to basically express the upper surface and lower surface in spherical coordinates. So we just substitute the x and y and z into the equation for the sphere and equate, and we'll finally get rho equals square root of 19. For the lower surface, we basically make the same substitutions for x, y, and z into this equation, and we end up with this equation. And so this can be simplified using a trig identity. Cos squared minus sine squared is cosine 2 phi. And if we then solve for rho, we get this is equal to the square root of secant 2 phi, because one goes into the denominator and 1 over cos is sec. The intersection between the two surfaces gives you the upper bound on phi. So if we equate this expression with this expression and simplify, so effectively cos 2 phi equals 2 cos squared phi minus 1 equals 119. So we've expanded cos 2 phi in terms of a trig identity. We would like it a phi value. This has got 2 phi. So this basically gets it into the situation we want it to be in, right? If you then take this and solve for phi, you'll get phi equals cos inverse root of 10 over root of 19. And the lower bound on phi will be 0. So phi equals 0 would be here, and phi equals cos inverse root 10 over 19 would be effectively this angle here. So phi equals 0, phi equals cos inverse root 10 over root 19. The range of theta will again between 0 and 2 pi since you're doing a full revolution. So as before, the differential volume basically is this, and rho squared sine phi is the determinant of the Jacobian matrix. And so just taking this information, the blues and the yellows, and we have the limits on phi, the limits on rho, or bounds on rho, and the bound on theta. And so we can now put together the integral. And so this is what I've done here. Lower and upper bound on rho, lower and upper bound on phi, lower and upper bound on theta. And if you perform this integral, you'll end up with this expression. Now, in this case, of course, when you integrate rho squared, you get a rho cubed. And so we'll end up with something that looks like this. And again, you can do this type of integral. I'm not expecting you to do it, but it turns out that it looks like this. Okay. All right, so we can visualize the different surfaces we're dealing with here. And so, for instance, red is the top and bottom surface for the inner integral. That's the bottom one and the top one. The yellow line and the yellow cone, there's the yellow line. That's at phi equals 0. And the cone would be phi at this value here. That's basically another two surfaces. And the third is the half-plane wedge. That makes a full rotation. In other words, if you look at the slider T, right, if you basically let that run, this wedge will just make a full circle all the way around. So this next problem, taken also from chapter 16.5, question 81, is a more complicated triple integral. So the statement is one sphere is centered at the origin and has a radius capital R. Another sphere is centered at 0, 0, small r and has a radius of small r, where small r is greater than capital R divided by 2. What is the volume of the region common to the two spheres? So in drawing, it's easier to use just a trace to visualize the problem. So if you were to basically take a plane that basically cuts through the origin, in any particular direction, you will find that you will end up with a picture that looks like this. So the trace shows circle of radius r and another trace, another circle of radius small r offset by distance r along the z-axis. And so from this image, it's very clear that in fact the region of interest is right in this region here. So you have the curve that you see here, and you have the curve that you see here. And we want to solve this problem in spherical coordinates. And so we make use of the transformations that allow us basically to express x, y, and z in terms of rho, theta, and phi. Now, in this problem, there's a bit of a problem because remember the rules for integration. We have to make sure that the boundaries are continuously differentiable. But if you were to look at rho here, rho would basically point to this contour as well as this contour. This contour is smooth, but the moment you reach this point, suddenly the direction changes. So at this point and this point, there's a discontinuity. Discontinuity as far as the derivative is concerned. And that means we have to break things up into regions. And the blue line basically is the dividing line between one region, which is above the blue line, and another region which is below the blue line. And so two integrals are required, and so we have to sort of be a little bit more careful in terms of how things are set up. All right, so that's the point that's made here. So for the upper surface integral, that's here, at the upper bound basically after substitution would be rho u equals r. So this is just the equation of a sphere, so rho u equals r. For the lower surface, we would use the cosine law. For triangles, r squared equals r squared plus rho l squared minus 2r rho l cos phi. Okay, cos phi basically being the angle in here, and we have an r that basically, this is a rho l, we have an r here, and we have an r here. And so you can express this length in terms of this length, and the angle between the two. And that actually is cosine phi. Anyway, if you simplify that, you get rho l equals 2r cosine phi. So the next thing to look at is what is the angle at which we could move from one region into another region? Well, that's determined by equating rho upper with rho lower and solving, which is what we're doing here, and then solving for phi, which then allows us to obtain the following result. Phi equals cos inverse capital R divided by 2r. So the lower bound, the lower bounds now in terms of, we've talked about the upper bounds for the upper surface integral, and for the lower bounds will just be rho u equals 0 and rho l equals 0. In this case, though, we have two different regions to consider. We know that the dividing line occurs at phi equals cosine inverse capital R over 2r. For this region, therefore, we go from phi equals 0 to phi equals cosine inverse r over capital R over 2r. And for the bottom region, we go from cosine inverse capital R over 2r to 590 degrees. That's pi over 2. So eventually, when we reach the point at the origin, we're basically pointing in this direction. So the angle phi, which is from here to here, would be 90 degrees. So that now allows us to set things up. Also recalling the differential volume, that this term here represents the determinant of the Jacobian matrix. So for integral 1, these are the bounds for phi, upper and lower. And for rho, these are the upper bounds, the lower bound and upper bound for rho, and these are the lower and upper bound for theta. For integral 2, which is basically going to be the lower branch that's below the blue line, the limits on phi, or the bounds, are cosine inverse capital R over 2r. Lower and upper is pi over 2. And rho will be between 0 and 2r cos phi, and theta basically extends from 0 to 2 pi. So this more or less basically is the setup for the problem, and in the next slide basically we just have to do the necessary substitutions into the triple integrals, and then we can solve the problem. All right, so I just put the things together. Here's integral 1. Again, bounds on rho, bounds on phi, bounds on theta. And this is the second integral, bounds on rho, bounds on phi, bounds on theta. And if you simplify, you do the integral, you'll end up basically with this answer, which is consistent with the results we had when we solved using Cartesian coordinates as well as cylindrical coordinates. If you would like to look at a picture of this, you can. So for instance, the top surface, which is the inner integral, is red. Purple is the bottom surface, this integral 2. And so the third would be the yellow, which is a line and a cone, this one and this one. That's the middle integral of 1. And yellow cone and gray plane. So that cone and the gray plane, it's the middle integral for number of integral 2. And blue is the half plane wedge for both the integral 1 and integral 2. That's for the outermost integral. In both of the cases where we're dealing with the top surface and the bottom surface, the value of rho for the lower limits is going to be 0. So you see a 0 there, and you see a 0 there as well. So this is more or less basically how we have solved this problem. We had to split it into regions because the rho was basically not continuously differentiable. And so by splitting in two, we could make each section continuously differentiable. Well, that concludes lecture 16C. And also this basically is completion of the first part of the course. Starting with lecture 17, we'll get into some new material. Anyway, thank you for listening.